that for two Hilbert spaces, we can define tensor products of two Hilbert spaces. We can mod out by the action of the symmetric group, but we have to be careful. In category theory, you don't want to say that two objects are equal, usually. You want to say that they're isomorphic. So when we mod out, you don't say that these two permuted tensor products are equal. We just insert an isomorphism, which I'm calling F sigma, between them. And then those isomorphisms, we want them to be coherent in this way. So this is slightly technical, but there's a way to take a category, have a group acting on it, and mod out by the group action. But the right way to do it is this weak modding out. It's not really technical. It just takes a little time to get used to. And so this will give you a new two Hilbert space, which will, however, be infinite dimensional, because n goes on up to infinity, typically infinite dimensional. So you can define creation operators and annihilation operators just as before. So now there will be, instead of a function, there will be a functor sending any object like this. I should have written some tensor product signs, I guess, to an object where we tensor with this additional object. And now there will be an adjoint functor going back, it turns out, and that's called the annihilation operator. And these will obey the same kind of relations, but only up to isomorphism. So in the ordinary Fock space, one way to write that interesting relation was that these don't commute. There's a correction term. So for example, kind of thing I'm saying is that ddx of x of f is x of ddx of f plus f. But now, in this categorified context, this functor and this functor are not equal to each other. They're naturally isomorphic to each other. So that finally, I reach a certain point here, which is this is supposed to be leading up to, which is we have these isomorphisms here, but you could ask, what new equations do those isomorphisms obey? So the way it works when you categorify things is you say, I had a set with some operations that obeyed some equations. Now I'm going to try to copy that idea, but now I'm going to use a category, and I'll have some functors, and they may obey similar equations up to natural isomorphism. So far it's not very interesting because it's sort of the same thing, but with fancier concepts. But those natural isomorphisms very often will satisfy equations of their own. And that's the new layer of structure that you can only see when you categorify. Maybe I'll give another example of that phenomenon. So when you first learn about the commutative law, it's an equation. When you learn about braided monoidal categories, you say they're categories where instead we have an isomorphism and between x tensor y and y tensor x, and we draw it in this nice suggestive manner. But then, see, it turns out that the interesting thing is when you now have three things and you start switching them, this braiding, this is called the braiding, it satisfies an interesting equation called the Yang-Baxter equation. Sorry, I'm not doing this very well. And this equation here turns out, in some sense, to be the key equation that's obeyed by the braiding. And it's something that you couldn't have guessed just by staring at this. Well, maybe if you're really smart, you could guess it by staring at this. But that's a new layer of structure that's revealed when we pass from commutative monoids to braided monoidal categories. And there are infinitely many such layers of structure. When you go from sets to categories to two categories and so on, you keep finding new things. So that's why that's the interesting thing. So a question is what happens here?